Okay, good evening all. I hope you can hear me and someone respond. Whether you can hear me and see the screen. So,
Yes, I can hear.
okay, thank you. Right, so we'll start. Uh, okay, so last time we did the introduction of the modular arithmetic subject. So today we are going to continue with that, and we are going to finish the topic. Okay. Right, so we are going to continue from this particular place, the rule number 3. Maybe we discussed rule number 3 last time. Anyway, I'm going to repeat from there. Of course, you must know what is meant by GCD. We discussed that last time also. For example, GCD of 16 and 12 is 4. Right, so GCD of 18 and 24 is 6. So what is the definition of GCD? GCD is the largest number that divides all the given numbers. So you have to find the largest number. Okay, largest number. For example, if it is 16 and 12, the largest number that divides, when I say divides, divide without any remainder, right? So that number is obviously 4, right? So if you take 18 and 24, the largest number that divides both 18 and 24 is 6. Therefore, we say the greatest common divisor of 18 and 24 is 6. So that anyway we discussed last time as well. Okay, right. So this is a small rule that we are going to discuss now. Let A, B, C all are integers. So now you must be familiar with these notations. Let A, B, C, that is all are integers, and suppose A into C equal B into C in mod n, right? Mod n. Then we can say that A is congruent to B mod n if GCD of C and n is 1. So that is first rule. Okay. The second rule says A is congruent to mod n divided by D if GCD of C comma n equal D. Right. So that if that is this when D is greater than 1. Right. When D is greater than 1. Right. So let's see some examples regarding that. Okay. So we know that 18 is congruent to 3 in mod 5. So that is obvious. Why? 18 minus 3, which is 15, is divisible by 5. Therefore, we can say yes, 18 is congruent to 3. And in other words, in the world of 5, 18 and 3 are the same, has the same value, same meaning, right? So now let's try to multiply it by number, right? So this says if A, and we are going to multiply it by another number. So actually this should have started something like if A is congruent to B mod n. Okay, so that line is missing there. Then if you multiply it by C, something like this. So let's say that value is something like 3, right? Something like 3. Or we can just write it like this. So 18 can be written as 6 into 3, right? Obviously 18 is 6 into 3. So 3 can be written as 1 into 3. Now you can see this is in the form of this format is there, right? So now C is your common value. Now this is A and this is B. This is B and 3 is your C now, right? C is your 3 now, and obviously this is your N. Now let's find out whether this property is satisfied. So the GCD of we have to take what? C and N, right? GCD of C and N. So what is the GCD of C and N here? C is 3, N is 5. The greatest common divisor of 3 and 5 is obviously 1, because no bigger number than 1 is going to divide both 3 and 5. By the way, if the GCD of two numbers are 1, we say that those are relatively prime. So that is the additional thing, right? So if GCD of two numbers are 1, we say that they are relatively prime. So that is not they are prime numbers. Obviously in this case those are prime numbers, but that is different case. We say that those numbers are relatively prime, right? Right. So now in this case you can see that yes, these are relatively prime, or the GCD of 3 and 5 is 1. right? So in that case we can say that A is congruent to B mod 10, right? A is congruent to B mod 10. That means 6 is congruent to 1 mod 5, right? 6 is congruent to 1 mod 5. So from here you can get there, right? If 18 is congruent to 3 mod 5, we can say that 6 is congruent to 1 mod 5. Why? We rewrite 18 as 6 into 3, 3 as 1 into 3. Now it is in this format, right? Now actually we use it in the other way. When the GCD of those two values, the C and N values are 1, we can say that A is congruent to B mod 10. Okay, so that is when GCD of those two values are 1, right? But if the GCD is not 1, rather different value, then we have to say, we can't say that A is congruent to B mod 10. Then we can say only A is congruent to B mod n divided by D, right? So here in this case it happened to be 1. Therefore we just say, rewrite, or we got a different expression saying C is 6 is congruent to 1 mod 5. Okay, now let's take a example where the GCD is not going to be 1, rather it is going to have a different positive value. Okay, right. So let's take this example. 65 is congruent to 5 mod 10. So that is obvious, right? Because 65 minus 5 is 60. 60 is divisible by 10. So therefore, yes, this is correct. Now let's try to write it in that kind of format. That means you have to make sure that both these numbers are multiplied by same number. So that is what is meant by multiplied by constant. So we are just going to rearrange this. So here you can see that we can write it like 13 into 5, right? 13 into 5 is equal to 1 into 5 mod 10. So we are not changing anything, we are just rearranging. So now you can see that the 5 is the constant. 5 is the constant, which is C in our case, and of course N is this one, this is A, and this is B. Now we have to again check the GCD before writing. Now let's find the GCD of C and N. So GCD of C means 5 and 10. So the GCD of 5 and 10 is, we can see that it is 5, because the smallest number that divides both these given numbers is 5. Now you can see that is not 1. So that is not 1. So therefore you can't just say A is congruent to B mod n, but that is a positive number. So therefore we can say A is congruent to B mod n divided by D, right? N divided by D. So that means we can say from here, this is our A, 13 is congruent to B. B is, in this case B is 1 mod, you can't just say 10, it is 10 divided by this value D, 10 divided by 5. 10 divided by 5 is 2. So therefore we can say that 13 is congruent to 1 mod 2. Right? 2. So that is how, so from one congruent we can deduce another congruent using this rule, right? Using this rule. If the GCD of C and N is 1, we can simply say A is congruent to B mod 10. If the GCD of C and N is not 1, rather it is a positive number bigger than 1, then it is A is congruent to B mod n divided by D. Okay, right. So that is something we can use to get from one congruent to get some other congruent values. Okay. So I hope that is very clear, right? So this is mathematics. In mathematics you don't have something called half clear, etc., right? Either it is clear or not clear. Okay, so this is not physics or chemistry or something, or maybe clear, right? Because those are fuzzy subjects, right? But this is maths. Either you understood or you don't understand. Okay, right. Right, now we are moving to a theorem, so which is mentioned in your syllabus, and you can see that this theorem is there in your syllabus. We call it So are you still having that issue? Not seeing the screen properly? That means not seeing the full screen. Okay. If you can see the full screen, that is fine. So one screenshot shows that it's not the full screen together with the other screen, right? Anyone else having that issue? What is me pin the screen? So usually this is how we do that other times also. I think some configuration changes to this one. Is it that everyone is seen like that? This or only some of you? Anyway, I will again reshare it. Stop sharing. Entire screen. It looks like some of you can see the full screen, some of you can't see the full screen. So that is a strange thing. Okay, so I don't know whether we are going to get the issue again. Right, anyway. Right, so we are now going to, if you get the issue again, just pin the screen. So can you talk and tell me how to do that? Where is that pin the screen? We can't find out where is that particular property is there. Yeah. So in other days we don't get this issue anyway. I don't know how to pin the screen. Can someone talk and tell me? Then I can just quickly do that. I don't see any option like that. So I have basically shared the entire screen. Okay, I'll reshare it again. Right, anyway, so let me know if it is continuing for all of you. I think it is happening for only few of you, right? Right. So let's move on. So now we are going to discuss another theorem which is mentioned in your syllabus as well. So that is called Fermat's little theorem. Okay, Fermat's little theorem. So at first you might get it a little bit confused. Don't worry too much about the theorem, right? So anyway, I will just read out the theorem for you. It's not a very difficult theorem anyway. If any integer a, right? So just let me know. For any integer a, if p is a prime number, right? If p is a prime number, then the number a to the power p minus a is an integer multiple of p, right? So that is what the Fermat's little theorem say. So sometimes we call it Fermat's little theorem, or sometimes we just call it Fermat's theorem because Fermat came up with a lot of theorems. So therefore, to distinguish his other theorems from this one, we just call it Fermat's little theorem, right? So it has nothing to do with the size or whatever. So the people has just named it as a Fermat's little theorem. Okay, right? So it's what it says is for any integer a, if p is a prime number, that's very important. If p is a prime number, then a to the power minus a is an integer multiple of p, right? So in other words, in a simpler way, we can say if p is a prime number, a to the power p is congruent to a in mod p. So that is the easier way of telling it. You can see this is same as this, okay? Right? So this is same as this. So when we say a to the power p is congruent to a mod p, that it means a to the power p minus a is divisible by p. Right, so same thing, right? So easier thing is remember this one. If you want to put it into words, you can always put it into words saying that a to the power p minus a is divisible by p, or a to the power p minus a is integer multiple of p, right? So when we say integer multiple of p, that means that is divisible by p, right? You can see this is another way of putting this into words, right? Putting this into words, but we have to make sure that this happens when p is a prime number. So that is very, very important. Okay, so let's take an example to identify whether that is going to be the case. Okay, right. So assume that our p is 7. Obviously p must be a prime number. 7 is a prime number. So a can be any integer. So let's say a equal to, right? So then you can say that 2 to the power 7, because we have to take a to the power p. 2 to the power 7 is congruent to a, that is 2 in mod 7. So that is the result of Fermat's little theorem, right? So we can say that since p is a prime number, a is an integer, we can say that using Fermat's little theorem, 2 to the power 7 is congruent to 2 in mod 7. Right? In the world of 7, both 2 to the power 7 and 2 are the same, right? So that is what, of course we can double check, right? So let's take the calculator and double check whether that is correct. So let's take the calculator. Of course, you must know that the calculator has this mod operation, scientific calculator. Right? So let's first calculate 2 to the power 7, 2 to the power x to the power y, 2 to the power 7, which is 128, right? So we have to check whether 128 and 2 are the equivalent in the mod 7. So let's take 128 mod 7. You can see that is 2. So that is why it says yes, 128 and 2 is equivalent or congruent in mod 7. Now you can see Fermat's little theorem is valid, right? Fermat's little theorem is valid. So if you want, you can just take another random prime number, take a random integer and just calculate and see whether it is going to be the same. So those things you have to do. Don't just accept things because someone told you or whatever, right? So always try out those things. Is it true, right? So something like that. So Fermat came up with this. So actually, not he came up with this. He found that this nature is there. This nature is there. So we call it the Fermat's little theorem. So you can see once you get little bit familiar with, you will see that this is not a complicated theorem, right? But when you just look at it, you will feel like, okay, it is a very complicated thing that this guy is telling. But you can see that once you spend some time, you have to do slow thinking, right? Slow thinking. Once you spend some time, you will find that, okay, this is, of course, this is a very useful thing, but this is not a very complicated thing. Okay, so if p is a prime number for any integer a to the power p equal to a mod p, or in other words, a to the power p minus p is an integer multiple of p, right? Integer multiple of p. In other words, a to the power p minus a is divisible by p. Okay, so you can put it in any words. Whatever the words you use, it means a to the power p is congruent to a mod p, right? So that you can use without any proof, because it's a theorem. Just like you use the Pythagoras theorem, etc. You can see you can use it. But only thing is, this is applicable when only when this mod is prime number, or for prime number modulus only this theorem is going to work. Okay, so that is something you have to remember. Okay, right. So there is a special case of Fermat's little theorem as well. That is, if A is not divisible by P, right? So there's another extra condition. Then we can say a to the power p minus 1 is an integer multiple of p. So that is a special case. So in that case, we can say that when a is not divisible by p, we can write this as a special case. Same thing, you can write it in a special case. Now a to the power p minus 1 is congruent to 1 mod p. Okay, so in other words, a to the power p minus 1, when you divide it by p, you get 1. Okay, so that is a special case, right? That special case we can use to calculate inverse of numbers, right? Inverse of numbers. If you have x, if you want to find the inverse of x, that's this special case of Fermat's little theorem we can use. Okay, so don't worry too much about remembering this one, because this is not the one we are going to use it. We are going to use variation of this theorem to easily calculate some inverse values. Okay, inverse values. But remember this one, because that is not difficult thing to remember. A to the power is congruent to a in mod p, as long as p is a prime number, right? And a is any integer. Okay, so we are going to use this the special case of this one when it comes to calculating inverse values. Okay, so there are different ways you can calculate inverse values. Use of this Fermat's little theorem is the easiest one, but the only thing is Fermat's little theorem can't be used for all the cases, only for special cases. Okay, right. So we can use Fermat's little theorem for two things. That is, you can use it to calculate very large numbers divided by prime number. If you want to find a very large number divided by prime number, what is the value of that, or what is the remainder of that, we can use the Fermat's little theorem. And of course, you can use Fermat's little theorem to in solving congruency equation. So we are going to do that as the last step today, as how to solve congruency equations. Okay, right. So we'll do few examples. So this one is mentioned in your syllabus also, so that is why I just put it, right? Finding the remainder of very large number divided by prime number, right? Very large number divided by prime number, how to calculate that value easily, right? Easily, because sometimes if it is a very large number, even your calculator is not going to work, right? Because calculators also have limitations, right? So therefore, using the Fermat's little theorem, we can calculate it, right? In a using a small tactic, we can calculate the remainder. Okay, so let's take an example. Assume that so we want to calculate what is the remainder of 2 to the power 16 if it is divisible by 17. Of course, this divisible number must be prime number, otherwise you can't use this approach, right? We can use this approach only when it is divided by a prime number, right? So this is a very large number, 2 to the power 16, right? It's a very large number. Of course, you can use it for small numbers as well. Only thing is, if it is a small number, you don't need to use the Fermat's little theorem, right? So this is a very large number, right? And this is a prime number. So we want to find out what is the value of the remainder if you divide 2 to the power 16 by 17. Okay, right. So now we are going to use that special case of Fermat's little theorem, that is a to the power p minus 1 equal 1 mod p, right? A to the power p minus 1 equal 1 mod p, right? So let's let a equal 2, because we are talking about now this is p, this is P, prime number, and let's take A as 2, right? So in that case we can write A to the power 17 minus 1, because P is 17, equal to, so of course 17 minus 1 is 16, that means 2 to the power 16 equal to 1 mod PP is 17, right? So that is something we deduce from the Fermat's little theorem, right? Because we took P as 17 because this is something to do with 17, and this is something to do with the 2 to the power. So therefore we are using the 2 here. So A as the 2, right? A as 2. So therefore from Fermat's little theorem we get 2 to the power 16 equal 1 mod 17, right? 1 mod 17. So therefore you can see that, so when we say 2 to the power 16 is congruent to 1 mod 17, so that means 1 and 2 to the power 16 are the same in mod 17, right? So that means when you divide 2 to the power 16 by 17, the value is 1, right? So the answer is 1. So you can see, without calculating what is the value of 2 to the power 16, by using the Fermat's little theorem, we found that the remainder is going to be 1. Right? Remainder is going to be 1. So that is why we say that if 2 to the power 16 and 1 is congruent, that means the remainder is 1. Right? Remainder is 1. So 2 to the power 16 divided by 17 is 1. Okay? Right. So just give me 1 minute. Hello Indika, මම ක්ලාස් එකේ ඉන්නේ. ඔයාලට පස්සේ ගන්නම් ආ. හරි. හරි. Right. So sorry about that. So I got a call. Right. So by using the Fermat's little theorem in a very handy way, or very tactical way, we came up with the answer without calculating what is the 2 to the power 16 is. Okay, right? So those kind of things we can do with Fermat's little theorem. Okay, so let's take another example, right? But the only thing is you can't do this for all the places, right? So you can do it when things are going to fit, right? When things are going to fit. Right, so let's take another example. So we want to find 2 to the power 15 when it is divided by 17. Right, again by Fermat's little theorem we know that. So last time also we written 2 to the power 16 equal 1 mod 17. So that is by using the Fermat's little theorem, taking P as 17, and taking P as 17 and taking A as 2. Right, so just by applying this we get this one. So anyway, in the last example also we did the same thing. Now this is 2 to the power 15, right? So last time it was straightforward. Now it is 2 to the power 15. Then we have to rearrange this number to use with this one, right? So what we have to do is we have to write it as 50 as, because that is 50, 16 into 3 plus 2. Right, 16 into 3 plus 2, because now we have this 16, we have this Fermat's little theorem gives the value for the 16. So therefore we can write 50 as 16 into 3, then the remainder is you have to add another 2, right? Another 2. So that you can rearrange it again. So now using that we can rearrange 2 to the power 50 as, because what we need is 2 to the power 50. We can say 2 to the power 50 is 2 to the power 16 to the power 3, because 16 to that multiplied 16 to 3 into so this must be 1 actually, not 2 to the power 2. This must be 2, right? This must be 2. Okay, no, so just one more 2 is there, so therefore you have to add that one again, right? Add that one again. Therefore 16 into 3, to that you have to add another 2 is there, so therefore you just say multiplied by another 2, right? Another 2. So then, right, then So now our equation is something like this. So this is something we all got from our Fermat's little theorem, that is 2 to the power 16 is congruent to 1 mod 17, right? So that is something we got it. Then we can write 2 to the power 16 to the power 3. So its third power is congruent to 1 to the power 3. So that we did, right? Remember, if a is congruent to b in mod n, we can say that any power of a to the power n is congruent to b to the power n in mod n. So we are using that rule. So that rule we discussed last time. Okay. So therefore we can say so we are taking the third power now. 2 to the power 16 to the power 3 is congruent to 1 to the power 3 mod n. So why we are interested in making it third power? Because you can get the 2 to the power 50 by doing this thing, right? So that is why we are taking the third power, right? And this rule we discussed last time. So therefore now you can write it as right? So therefore we can write it like this: 2 to the power 16 to the power 3 is 1 to the power 3 mod 17. Okay. So then we have to multiply it by 4 again, because what we need is not 16 to the power 3. We want the 50, right? Here what we get is 48. So what we need is 50. Therefore we multiply again by 2 to the power 2. But we have to do it in both sides. Remember, if we have a is congruent to b mod n, we can multiply both sides by the same value. That rule we discussed last time. So we can, therefore it's not going to harm. We are again multiplying it by 4 also, right? So that make this side 2 to the power 50, and this side it is now 4, because 1 to the power 3 is 1, so therefore it is 4. Now you can see that 2 to the power 50 is now somehow from this one we managed to get this one by applying the valid modular arithmetic rules, right? By applying valid modular arithmetic rules, we managed to get from here to here, right? Now it says 2 to the power 50 is congruent to 4 in mod 17. So that means, right, when you divide 2 to the power 15 by 17, the remainder is 4, right? So now we found it. So that is our original question. What is the remainder value when you divide 2 to the power 15 by 17, right? So the answer is 2 to the power 15 is congruent to 4 mod 17. That means, obviously, when you divide 2 to the power 50 by 17, you are going to get the remainder as 4, right? So that is how you get it. So idea is, of course, this is not going to work for all the questions, right? Only for special cases you can use it. Just identify. So of course the mod has to be prime number, so take it as a prime number, take it as the a. From there you come up with this formula using the Fermat's little theorem. Then try to get this one by applying valid modular arithmetic rules. So usually you have to write it like this. Then you should be able to from here you should be able to get into this one. So then the right hand side has the answer. Okay. So I did 2 examples. I think I have given you one more example. Yes, so that you can do. There are few more examples given, because in your slides also they have given so many examples, I think. Modular arithmetic. Chapter 8. Yes. Right, so you can see so many examples they have given. 2 to the power 2020, whether it's divisible by 14 one, right? So things like that, big values, right? Right, so we have to use this Fermat's little theorem. Okay, So actually what we are using is this second version, or the rather than this version. In this case we are using the second format of the Fermat's little theorem. Okay, right. So I have given you a few more examples, so you can just go through that, and of course you can go through your examples given in the slides as well. Okay, right. So now we are moving to another important topic, that is Euclidean greatest common divisor algorithm. Right, so it's another algorithm. So those are the two algorithms that we have. The Fermat's little theorem that we did, so it can be represented in two ways. The second important theorem, it's not actually theorem, it's algorithm. So that is called Euclidean Gcd algorithm. So this is an algorithm that we can use to find greatest common divisor. Of course, finding GCD is not a big thing when we have small numbers, right? For example, if someone gives something like 24 and 18, so obviously you can just, after spending a few seconds, you can say that okay, the answer is 6, right? Answer is 6, because that is the biggest number that divide both 24 and 18, right? So if you take something like 36 and 18, right? So what is the again? So that that time it's going to be what? It's going to be 9, because it's not 6 now, right? 9 is bigger than 6. 18 is divisible by 9, and 36 is divisible by 9. So therefore it is 9. But that can be done when you have relatively small numbers. But when you have very big numbers, right? So that is not going to work. You have to spend some time finding the value. So Euclidean came up with a smart idea to find this GCD value of big numbers. Of course, it can be applied to any number. It's especially helpful when these numbers are really big. He came up with an algorithm, right? So that is called Euclidean Gcd algorithm. Again, don't memorize this formula, algorithm, or the formula, because it's I don't know, if you have really good memory, that is okay. But usually you don't have to memorize this algorithm. Anyway, I just read out the algorithm. If x divides a and b, x also divides a minus k into b for every k. Right? So you can say it's weird thing. So what you want to understand is not to memorize this, but just try to understand how we can use the Euclidean algorithm. So one easier thing is, rather than concentrating on this one, just let's see an example how to find the GCD using Euclidean algorithm. So once you understand it, you will find that okay, that is not a big thing. Forget about the definition. We'll find the GCD. Okay, right. So let's say that we want to find the GCD of 39 and 15, and obviously that is a two small values. By looking at the numbers also, you can see that obviously that number is 3. Okay, because no number bigger than 3 is going to divide both 39 and 15. But anyway, to get familiar with the Euclidean algorithm, let's use the Euclidean algorithm to find the GCD of 39 and 15. Okay, so it's very straightforward, very simple. Once you get familiar with the Euclidean algorithm, right? So what you have to do is take the bigger number of the given numbers. Always when you are given two numbers, you can find which one is the bigger number. So in this case, the bigger number is 39. So then what you have to do is you have to write it as 39 equal constant time 15 plus value. So that means you have to make sure that when you multiply it by 15, you get very closer to 39. Then you have to add something smaller than 15, right? Something smaller than 15. So what is that value? Obviously 15, then 30. So 45 is anyway bigger than 39. So therefore we have to say it is 2 times 15. Now it is 30, and now just we have to add 9. Right? So we didn't say 1 times 15, then we have to add more than 15. So it has to be additional value must be less than 15, right? And it must be positive value, not a negative value, right? So therefore, obviously, now you can say 39 equal 2 times 15 plus 9. So now we are going to repeat this again. So now you have to take this value, right, and you write it here. Then you try to do the same thing. Now the multiple must be 9, right? So multiple must be 9. So then how many times you multiply it by 9 and added something, you get 15. Obviously it is 9 into 1, because if it is 9 into 2, it is bigger than 15. You can't subtract, you have to always add. So therefore it is going to be 1. 9 into 1 is 9. Now you have to add 6 more, right? So again we have to repeat this. Now this 9 you are going to take here. Now it has been multiple of 6, right? Multiple of 6. Now you can see there's a pattern. This guy comes here and this guy comes here, right? So this guy comes here, so therefore this guy comes here, right? 6 into how many times? It's again going to be 1, because 2 is bigger, right? So then we have to add 3 more, right? So you have to keep doing this until here you get 0, right? Here you get 0, still it is not 0. So again we have to repeat now, right? Again we have to repeat now. So now we have to take this guy here. 6 equal how many times this guy? Obviously 6 is 2 times 3, right? Oh, now I don't have to add anything, and now it is 0. So when you get into 0, you can stop. You can stop, because now you got that magic number 0, right? Then the GCD of the 39 and 15 is this value, right? So this value. So that is how you do that. Okay, so you keep doing this until you get 0 here. When you get 0 here, your GCD is here, right? GCD is here. Okay, right? So that is how you do that. Always start with the bigger number here, a smaller number here, right? Then keep doing until you get 0 here. So that is not difficult thing. Once you get to know it, you will find that okay, you need to put some effort. Until you get into 0, you have to do that, but it's just a simple thing. And of course it's a very good thing, since you have done some programming. You can just write a Java program, right? So you can just write a Java program when you are given the two numbers, right? When you are given two numbers, you can return the GCD. So that you can just write your code and post to the WhatsApp group if you like. Okay, so even now itself you can do it, right? Now itself within maybe 10-15 minutes, if you are really good at in Java. So just take it as a challenge. So don't do that now just concentrate on the subject today, right? So after the session, maybe before midnight, 12 o'clock, so I expect at least one person post that code to the WhatsApp group. Okay, so it's something like this. It's returning int, say calc GCD, and you have two integers, int x, int y. So you have to write the logic. You have to write the logic using the GCD algorithm, right? GCD algorithm. So that can be done. That can be done. Of course, you can use a recursion as well, or you can just go for a loop. Right? Use of recursion is going to be more elegant solution, but even a loop is going to work, right? So just then you will better understand what is Euclidean algorithm is. Okay, right? So let's take one more example. So I have given you a few more. Right, so anyway you have to find out the GCDs when you are solving other things as well. So let's take another example. Find the GCD of 1030 and 960. Now you can see it's somewhat bigger. It's not easy to guess because we never know is there a bigger number than that which is going to be your GCD, right? Right. So now let's do that. So take the bigger number here, 1030. Now you have to write it as a multiple of 96 plus something. Obviously you can see it is 1, because if you multiply it by 2, it's bigger than 1030. So when you do it with some feeling, that is not difficult, right? So but you have to live with that, right? So 1 into 960, then we have to add 70 more, right? 70 more. Still this is not 0, therefore we can't stop. And now what we have to do is we take 960 here. Now you have to write it as a multiple of 70, right? Multiple of 70. So how many? So that you have to guess. So in this case it is going to be 10 is 700, so you have to keep adding, it will be 13, and then you have to add 50 more, right? 50 more. Still this is not 0, therefore you have to keep doing. Now take 70 here. Now you have to write it as a multiple of 50, right? That is now easy. It is obviously going to be 1 and plus 20. Now still you can't stop, because until you get it here 0 you can't stop. Again now take 50 here, and now you have to take it as multiple of 20. Now it is easy. Now obviously it is multiple of 2, because 20 into 2 is 40. Just you have to add 10 more, right? Now again you have to do it. 20 is how many multiple of 10, because 10 you have to take it here. So it is going to be 2, and now it is 20, and now we can stop because now it is 0, right? So by the time this value is your GCD. So the GCD of 1030 and 960 is 10, right? So this can be done to any number, right? So this is a very general approach. If you take any number, even millions or billions of number, the two numbers are in the order of millions or billions, still when you do this, ultimately you are going to get the value, right? Ultimately you are going to get the value. So therefore this is very handy, the Euclidean algorithm, to find the GCD, right? Especially when the numbers are really big, so that we can't just guess it, okay? Right. So why we are interested in GCD, you have already found that there are places we need GCD, right? So there are places we need GCD, and right, so you can see, so these cases we have to check whether the GCD is 1, right, or what is the GCD of the value, right? Then only we can apply these things. So therefore GCD is really important. And also, so later today also we are going to use GCD to find the inverse values, right? Inverse values. So today, so far we have found one way to find the inverse values of actually still we haven't used it. So using the using the Fermat's little theorem, so we just did one usage of Fermat's little theorem, that is finding the remainder when you have big number and prime number. So the second use of Fermat's little theorem is finding the inverse value. So you can use the Fermat's little theorem to find the inverse value, and also we can use this Euclidean algorithm and the GCD to find the inverse of a value. So therefore that is another reason why we are interested in Euclidean algorithm, because finding GCD is going to be really helpful, especially finding inverse values, okay? Right. So actually that is our so there's a small mistake here. It must be inverse, right? Inverse of a number, okay? Right. So that is exactly what we are going to do right now. How to find the inverse of a number, right? How to find the inverse of a number, right? So now let's try to understand what is mean by inverse, right? What is mean by inverse? So usually we write the inverse as something like this. By the way, anyway, if you have do you have any questions up to now? Because I am doing a little bit faster because I want to finish it today, okay? So because we did very slowly, we did last time, right? Very slowly I did. So today I'm going to do it very fast, because now based on top of that understanding, we are building this, okay? Right. So any questions up to now? Because you can't have any doubts, right? In maths, either you know it or you don't know it. There's nothing called halfway. Right. So let's move on to the inverse then. Right. So what is mean by inverse? So you will see the term inverse in so many places. Those who have done A-level maths, they have seen this so many places, right? So those who have not done A-level maths, they have seen the inverse in only one place. That is when we say 5, the inverse of 5 is 5 inverse, so 5 to the power minus 1, we know that, so let's take it in a proper way. If you take 5, the 5 inverse is called 1 over 5, right? If you take something like 10, the 10 inverse is 1 over 10, right? So that is inverse, right? That is inverse. So that is why we write inverse of 5 as, because we know that 1 over 5 can be written as 5 to the power minus 1, right? 5 to the power minus 1, because this is 1 to 1, so you know that minus, when you have a power in the denominator, you can just take it to the numerator and say it's a negative power. So that is a to the power minus n is 1 over a to the power n, that you learn in this first topic. Okay, right. So therefore we can say that because inverse of 5 is 1 over 5, we just write inverse of 5 as 5 minus 1. So that we use it as a sort of a notation, because that is going to work anyway, because inverse of 5 is 1 over 5. 1 over 5 can be written as 5 to the power minus 1. Okay, so that is called multiplicative inverse, right? Multiplicative inverse. So if someone asks what is mean by inverse, now can someone give me the definition? What is mean by multiplicative inverse of a number? So now it's your turn to talk. So if we have a number called x, what is mean by x inverse? So very simple definition. Right? So the answer is very simple. Inverse of a number is the number when you multiply it by that number. If you get 1, we say that is the inverse of x. Or so rather than say y, I can say if we find a number, or if you have found x inverse, when you multiply x by the inverse, you must get 1. So that is how you double check whether actually you have found the inverse. Right, so then now you can see that why we say inverse of 5 is 1 over 5, because when you multiply it, you get 1. Right, so therefore inverse of a number is a number when multiplied by that number, you get 1. So in that case, we say that second number as the multiplicative inverse, right? Multiplicative inverse, and one is called multiplicative identity. Right, so these terms are really important. So I'm again repeating. If you have a number and if you multiply it by another number, if you get multiplicative identity, right? So multiplicative identity is 1. Multiplicative identity. You know what is identity? Identity means 1. Identity. So if you multiply a number by another number and if you are getting the multiplicative identity, then the second number is called multiplicative index, multiplicative inverse, or you can just say that is x minus 1. Okay, so that is how you define the multiplicative index, multiplicative inverse, right? So those who are doing maths in your final year, you will find there's another concept called inverse of a matrix, right? Inverse of a matrix. So likewise, this concept called inverse is there everywhere in mathematics, right? Everywhere in mathematics you have this concept called inverse, right? So therefore this is very important thing, right? So then we have another type of inverse called additive inverse. So this is multiplication. So this is the inverse with respect to multiplication. So what is the inverse of a number with respect to multiplication? 1 over that number, right? If it is 5, the inverse, multiplicative inverse is 1 over 5, because when you multiply 5 by 1 over 5, you get the multiplicative identity. Multiplicative identity is 1. So therefore 5 inverse is 1 over 5, right? But the concept called inverse is not only for whole numbers, it is there for fractions as well, right? For example, if your number is 2 by 3 or 2 over 3 or 2 upon 3, what is the what is the number that you multiplied by this number, you get 1. That is obviously 3 upon 2. 3 upon 2, because then it is going to be 1. So therefore we can say that inverse of 2 upon 3 is 3 upon 2, right? 3 upon 2. So likewise the concept called inverse is there even for fractions as well, right? So now I hope you get what is meant by multiplicative inverse, right? So the second type of inverse is called additive inverse. Additive inverse. Additive inverse is again the same definition I am going to use. If there is a number, right? If you now that is not this is not multiplicative. If there is a number, when you add a particular number, if you get additive identity, so additive identity is 0, that number is called additive inverse of that number, right? So now you can see that the two definitions are pretty much the same. So this is additive inverse definition. If you have a number and if you add, that is why we say additive inverse, add a number to that, and if you are getting the additive identity which is 0, then that number is called additive inverse. How to define the multiplicative inverse? If you have a number and if you are multiply by a number, if you are getting the multiplicative identity which is 1, then that is the multiplicative inverse, right? Multiplicative inverse. So for example, if it is 5, the multiplicative inverse is 1 upon 5, right? Because when you multiply 5 by 1 by 5, you get 1. So now you can see if the number is 5, what is the additive inverse? Obviously it is going to be minus 5, because when you add 5 with minus 5, what you get is 0. So therefore additive inverse is its negative value, right? For example, if it is 3, additive inverse is minus 3, because when you add minus 3 with 3, you get additive identity which is 0. Okay, right? But we are more interested about the multiplicative index, multiplicative identity, right? Multiplicative identity rather than the additive identity, sorry, additive inverse. So we are more interested about the multiplicative inverse rather than additive inverse. Okay, but there's some concept called additive inverse as well, right? Additive inverse, additive identity which is 0, and multiplicative index inverse and multiplicative identity which is 1. Okay, right? So now we are going to extend that concept to modular arithmetic as well. So that is normal arithmetic. That is normal arithmetic. Now we are going to extend that the concept called, now we are more interested about the multiplicative inverse and multiplicative identity, right? Not the additive one. Okay, right? Now let's assume we are not talking about the mod 10 or the normal mod or the normal base 10. Assume that let's take an example. We are interested in mod 5. So I am now again doing very slowly because I want to explain you a concept, right? Concept called inverse. Okay, so we are not hurried, right? If you hurry, you try to without understanding, you just try to get some things. Okay, get some materials. Right, so assume that it is mod 5. We know that if it is mod 5, the possible numbers are 0, 1, 2, 3 and 4. Right, so that is what I mentioned in the very first thing in the session. If it is mod 12, 0 to 11, so don't get fooled by looking at the clock. That there it is 12 is there. That is just to make you feel happy. Right, so because these concepts were before modular arithmetic concepts were built, people have already used the number 12 rather than 0, right? So therefore in proper arithmetic, if it is mod 5, what we have is 0 to 4. Now let's see. Now remember what is the definition of multiplicative inverse. From this moment onward, when I say inverse, I mean multiplicative inverse, right? I am not going to refer to additive inverse because we are interested in only multiplicative inverse. So what is the meaning of inverse? Multiplicative inverse, when you have a number, its multiplicative inverse is you have to find another number. When it multiplied by those two, when those numbers are multiplied, you get 1. Now let's see. In mod 5, how to find the multiplicative inverse of a number. Okay, right. So for example, if you take 1, so forget about this one, so I'm only interested about this one. If you take 1, if you multiply it by 0, you get 0. If you multiply it by 1, you get 1. If you multiply it by 2, you get 2. If you multiply it by 3, you get 3. If you multiply it by 4, you get 4. So therefore, what is the inverse of 1 in mod 5? It is 1. Because 1 multiplied by 1, what we get is 1. So therefore, I can say inverse of 1 in mod 5 is 1. Right? Is 1. Now let's take 2. When you multiply 2 by 1, what you get is 2. So therefore, inverse of 2 is not 1. Right? When you multiply 2 by 2, what you get is 4. Therefore, inverse of 2 is not 2. Because it is, if you get the inverse when the multiplication is resulting in 1. When you multiply 2 by 3, what you get is 1. Why we say what you get is 1? 2 by 3 is 6. But 6 is congruent to 1 in mod 5. Right? 1 in mod 5. So in the world of mod 5, 6 and 1 are the same. So therefore now you can see that when you multiply 2 by 3, it is 6, which is equivalent to 1. Therefore what you get is 1. So therefore I can say that inverse of 2, right? Inverse of 2 in mod 5 is what? 3. Right? In mod 5. Right? So now you can see that is different from normal arithmetic. In normal arithmetic, inverse of 2 is half. But in mod arithmetic, in modular arithmetic, anyway we don't have fractions, right? In modular arithmetic, in mod 5, inverse of 2 is 3. So that you have to understand, that you have to feel it, right? Right? So the reason is when 2 is multiplied by 3, which is 6, obviously 6 is equivalent to 1 in mod 5. Therefore, inverse of 2 is 3. Right? So that is how you get it. Right? Now let's see, if you multiply 2 by 4, what you get is 6. Right? What you get is 6. What you get is 8. 8 is equivalent to or congruent to 3, which is not 1. Therefore, we can say inverse of 2 is 4. So obviously, inverse of 2 is what? 3. Right? Inverse of, now we found that inverse of 1 is 1. Right? Inverse of 2 is 3. Why? When 2 into 3 is equivalent to 1. So now similarly, inverse of 3 is going to be 2, because 3 into 2 is 6. Right? And inverse of 4 is, now let's multiply it again. 4 into 1 is 4. So therefore 1 is not the inverse of 4. Right? 4 into 2 is 8. 8 is equivalent to or congruent to 3. Therefore 2 is not going to be inverse of 4. 4 into 3 is 12. 12 is congruent to 2. So therefore 3 is not going to be inverse of 4. 4 into 4 is 16. 16 is congruent to 1, because 16 minus 1 is 15. 15 divided by 5. Yes, 15 is divisible by 5. Therefore, yes, 4 into 4 is congruent to 1. So therefore now I can say that. Right, now I'm going to just mention these things. So now you have to just concentrate on where we get 1. Where do we get 1? Now by using this one, you can write that 1 inverse is 1. 2 inverse is 3. 3 inverse is 2. And 4 inverse is 4. But remember, this is in the world of mod 5 only. Right? Mod 5. Right? So now you know how to find inverse of a number. So you have to find the counterpart, its pair, where when you multiply those two, you get 1. Right? Congruent to 1. Congruent to 1. It's actually not 1, it must be congruent to 1. Right? So therefore, we can say that inverse of 3 in mod 5 is 2. Right? So if you are given a different modulus, like modulus 6 or modulus 4 or modulus 8 or whatever, similarly you will find some other inverse values. It's a good exercise for you to do. Something like take inverse of 6 or say take mod 6, then it will be 0, 0, 1, 2, 3, 4, 5. Here also 0, 1, 2, 3, 4, 5, and try to find out when you multiply say 3. If you want to find the 3 inverse, when I multiply it by which number, I get the congruent to 1. So that is your inverse of 3 in mod 6, right? So likewise, right? So that can be done, but that is not a very easy thing as well. So that is that. So we did this to understand what is mean by inverse, right? So when I say inverse, it is multiplicative inverse. So similarly, if you want, you can find the additive inverse also. That is, this is the additive inverse. For example, if you take 2, if you add 4, you get 1. So actually in additive inverse, usually what we take is not the 1, what we take is 0, right? Not the 1, because then we can say that additive inverse of 1 is 4, because that is what make it 0. Additive inverse of 2 is 3, that is what make it 0. Additive inverse of 3 is 2, that is what make it 0, right? Because 5 mod 5 is congruent to 0. Additive inverse of 4 is 1, right? So that concept is there for even for addition as well, but we are interested only in, just remember that is for your information I gave you, right? But we are only interested in multiplicative inverse, right? Multiplicative inverse. Okay, right? Now I hope you understood or you have a very good feeling. හරි අපි ගන්න ඉගෙන ගන්න දේ නිකන් ඇඟට දැනෙන්න ඕනේ හැංගීමක් ඇතුළේ නැත්නම් දර ගොඩවල් වගේ. හරි ගණන් හදනවා අර කැල්කියුලේටර් එකෙන් දර ගොඩන්නේ නේද? කැල්කියුලේටර් එකෙන් මෙලෝ වැඩක් නැහැනේ. කැල්කියුලේටර් රුපියල් 3400 ගණන් හදනවා. හරි ගණන් හදනවා. ගණන් හදන දර ගොඩවල් වලින් අපිට වැඩක් නැහැ. So we need people who can feel a concept, who can understand a concept. Okay, right? So yes, now you know what is meant by inverse. Now what we are interested is try to find a way of finding inverse value, because inverse values are really helpful in solving equations, right? Solving equations, the inverse is really important thing. So those who have done A level maths, they know that finding inverse is really important when you solve linear equations, right? Linear equations, simultaneous linear equations. So then they know this, right? So we have equations, say A inverse into, say if you have AX equal B or something, A inverse into something is something කියලා අපිට එනවා. මෙතන එතකොට මේ A ගේ inverse එක හොයාගත්තට පස්සේ අපිට මේක decom solve කරන්න පුළුවන්. Matrix පැත්තේ. Anyway, you are going to learn this in your final year maths. If you are interested in your final year maths, because now for you guys the maths 2 is in your final year, you will learn using matrices also how to find the inverse matrix and solve linear equations. So therefore, if you haven't understood what is mean by inverse, again you are going to be stuck in final year, right? Stuck in final year. So there is no other way than understanding things. Okay, right? So now I hope you got what is mean by inverse, right? So you are going to get more and more about inverse if you are doing final year mathematics as well, okay, in the matrices, right? So let's move on. So this is a interesting property, and very important property as well, right? An integer a has a multiplicative inverse modulo n. That means a has a multiplicative inverse in module n. හරි බරකලා කියන්න නැත in modulo n, if and only if GCD of a and n is 1. So that is a very important property. So that means not every number is going to have an inverse. Only some numbers have inverse. So that is interesting property, right? So usually when in normal arithmetic, when I say 10, you know that inverse multiplicative inverse is 1/10. When I say 4, you know that multiplicative inverse is 1/4. Even for fraction, when I say 3/2, you know that the multiplicative inverse is 2/3. Now you can see in normal arithmetic, every number has a multiplicative inverse. But in modular arithmetic, not only numbers are having, or not all the numbers are having its inverse. Only some numbers are having inverse. So those who have done A-level maths, they know that not every matrices are having inverse matrices. Only some matrices having inverse matrices. Now you can see that these things are really correlated, right? So that is what makes mathematics really interesting. Okay, right? So those that statement is for those who have done A-level maths. Okay, right? Anyway, you will be encountering that in your final day if you are doing maths. Okay, right? So this theorem, or this is not a theorem actually. So a number has an inverse in a module n if and only if that value, that number and the module, if you take the GCD of those two, if it is 1 only, it has a inverse, otherwise it doesn't have inverse. So that means not all the numbers are going to have their inverse values, okay, in modular arithmetic. Okay, right? For example, let's take module 6, right? Modulo 6, right? So just like the previous one, so I'm interested in multiplicative multiplicative inverse, right? Multiplicative inverse. So let's see, let's take 1. So if I multiply 1 by 1, I get 1. So therefore obviously 1 inverse in mod 6 is 1, right? Is 1, congruent to 1. But if you take 2, if I multiply 2 by 0, that is 0. So what I need is 1. 2 by 2, that is 4. No. 2 by 3, that is 6. 6 is congruent to 0 because of now remember we are talking about mod 6. Right? So therefore still it is not 1. Right? Then if I multiply it by 4, 4 into 2 is 8. 8 is congruent to 2. So still not going to work. If I take 5, because 5 is also there because mod 6. 5 into 2 is 10. So 10 is congruent to 4. So you can see none of the time I got 1. So that means in mod 6, 2 doesn't have an inverse. 2 doesn't have inverse. So that is what this theorem also saying, right? So that theorem says that. Now let's see whether that, according to that theorem, whether it's going to have inverse or not. It says integer a has multiplicative inverse modulo n if and only if GCD of a and n is 1. Now let's see GCD of a and n is 1 or not. Now this, in this case, n is 6. Right? N is 6. Now we are interested in this scenario. Our a is 2. Our a is 2. Now what is GCD of n and a, or a and n? 2 and 6. GCD of 2 and 6 is 2. Now you can see obviously that is not 1. So this theorem say, not theorem actually, this property says if it is not 1, right, you have an inverse only if it is 1. Obviously in this case it is not 1, therefore 2 doesn't have an inverse in module n, right? But if you take something like, so you can try out these things, but if you take something like 5, now let's say GCD of 5 and 6. So this is my a, this is my n. Obviously that is 1. That means 5 has an inverse in mod 6. Right? 5 has an inverse in mod 6. Right? So if you just list down, if you just list down these things, right? So 1 and 6, 1. GCD is 1. 2 and 6, GCD is 2 because the module is 6. 3 6 module GCD is 3. 4 6 GCD is 2. 5 6 GCD is 1. So that means 1 has a inverse, multiplicative inverse. 1 has a multiplicative inverse. Then 5 has a multiplicative inverse. 2, 3 and 4 they don't have a multiplicative inverse. So only 1 and 5 has multiplicative inverse in the module 6. Now you can see only 1 and 5 has, you can see there's 1 here, there's 1 here, here there's nothing, no combination resulted in 1. So you can see that. So that is a very handy thing. By just applying this, you can see whether that is going to have a multiplicative inverse or it is not going to have multiplicative inverse, right? For example, if you are given to find inverse of, say, inverse of 8, in mod 10. Now can you tell me, is it going to have an inverse or no? It's not going to have inverse. Can someone tell me? So you just have to find out what is the GCD of 8 and 10. So obviously GCD of 8 and 10 is 2, which is not 1. Therefore I can say 8 doesn't have an inverse in mod 10. Right? 8 doesn't have inverse in mod 10. But if you take something like 8 inverse in mod, right, in mod 11, now you can see that GCD of 8 and 11 is 1. So therefore yes, 8 has an inverse in mod 11. So the first thing is you have to find out whether there is an inverse or not. If there is no inverse, you don't have to spend time finding the inverse. You can just say there is no inverse. So that is handy, right? That is handy. Otherwise, you will spend a lot of time to find out whether there is an inverse. Then only you find that okay, there is no inverse. So first thing is identify whether using this particular rule, identify whether there is an inverse or not, whether there is a multiplicative inverse or not. Okay, right. So now I hope you got the idea about inverse and also how to check. Now you know these things. In modular arithmetic, inverse is somewhat tricky, right? It is not as straightforward as normal arithmetic, and also not every number is going to have inverse. Only some numbers are going to have multiplicative inverse that you can always check by finding the GCD of that number and the modular value. If it is 1, yes, it has an inverse, otherwise it doesn't have a multiplicative inverse. Okay, right. Now let's discuss some ways of finding the multiplicative inverse. Okay, now you know what is multiplicative inverse and you know how to check whether a particular number has an inverse or not in a particular mod. Right, computing inverse of a prime number. Right, so we are interested in computing inverse of prime numbers. Right, prime numbers, not everything. Right, not everything, especially the prime numbers. Okay, right. So as I told you, there are two approaches. First one is use of Fermat's theorem. Right, so we have already used Fermat's theorem to find whether there is a what is the remainder of a very big powers, right? So that is the first usage. Now we are going to use the second usage of finding the inverses using the Fermat's theorem. So we have another approach as well. So this is the very easier one. So this is the easier one, but this can be done only when your value is a prime number. So that is a limitation. So therefore, don't think that this is going to work for everywhere. For general case, we have another approach, right? Especially the Euclidean algorithm can be used to find the inverse in a more general way. But if you can use Fermat's little theorem, or if the Fermat's little theorem is applicable, always that is the easiest way, right? But it is not going to work for all the cases, because it's going to work only when your number is a prime number, right? When your number is prime number. But in the exam also, just double check whether the given number is a prime number. Then don't waste your time using the Euclidean approach. You can just use the Fermat's little theorem. Okay, right. So if your number is a prime number, right, let P be a prime number, right? And if you want to find the inverse of P, sorry, let P be a prime number. That means it is applicable only when not the number is prime, when the mod D is prime. So I made a small mistake. So so this can be used only when you are working with modulus of prime numbers, like mod 3, even mod 2 is okay, because 2 is a prime number. Mod 2, mod 3, mod 5, mod 7, mod 11, mod 13, etc. In that case only this is going to work, Fermat's little theorem's variation. So there it says, let P be a prime number. So this must be a prime number. If you want to find the inverse of a number, right, inverse of a number on that mod which is a prime number, from Fermat's little theorem we can deduce that its inverse equal a to the power p minus 2 in mod p, right? So it's very simple, very straightforward to find it. So that is why I told you, if they are talking about a base or mod which is a prime number, you can always use this approach. Right? So just its inverse is a to the power p minus 2 mod p. Okay, mod p, right? Right. So let's use that and see whether we got the correct answers last time, because we did manually we calculated prime numbers here, right? So here, so let's use. So can I apply this to mod 5? Can I apply Fermat's little theorem here? Yes. Why? 5 is a prime number. So in our case now p is going to be 5. You can see in this case mod 5 I can use the Fermat's little theorem because now p is a prime number. Now let's say what is the prime inverse of 1? 1 inverse equal, right? A is now 1. 1 to the power p is 5. 5 minus 2 in mod 5. So we know that 5 minus 2 is 3. 1 to the power 3 is 1 anyway. So therefore 1 inverse equal 1 in mod 5. So that is exactly what we got. 1 inverse is 1. Right? 1 inverse is 1. Now let's apply this for 2. So what we got is 3. Right? So let's apply. Right. So let's say now our A is 2. I want to find 2 inverse. Of course in mod 5, which is a prime number, so therefore I can use Fermat's little theorem. That is 2 to the power 5 minus, so this is not p minus 2, p minus p minus 2, right? P minus 2, that is 5 minus 2, 5 minus 2, right? So let's take, that is 2 to the power 5 minus 2 is 3. 2 to the power 3 is 2, 4, 8, that is 8 mod 5, and we know that 8 mod 5 is when you divide 8 by 5, what is the remainder, which is 3, that is 3 mod 5. So that means inverse of 2 in mod 5 is 3. So that is exactly what we got, right? Inverse of inverse of 2. So when you have 2 here, what you get as multiplication as 1 is 3. Now you can see, yes, inverse of 2 is 3, correct? Right? Inverse of 2 is correct, right? Is 3. So similarly, if you apply it for 3 and 4, always you will get some value which is the same as from your this one. Okay, so now you can see that rather than writing this and try find out the inverse value, if it is something like mod 5, mod 7, mod 11, we can straight away find the inverses by using Fermat's little theorem. That is A inverse equal p a to the power p minus 2 mod p, a to the power p minus 2 mod p. Okay, but this can be done only when your mod value is, or your mod base is prime number. Okay, right? So that we are done. So if you have any questions, you can ask. Okay, right? So this is another approach. Right? This is another approach. So I am giving you few approaches. You can pick whichever you like, right? But formal approach is this one. Right? Formal approach is this one. You see Euclidean algorithm. But if you can find using any other approach faster than that one, why not using it? Okay. And also when you know so many ways of getting to the answer, it will help you understand the subject better, because you know that this way also it can be done, that way also it can be done, and so many ways you can, right? So the second approach is something like this. Say you are supposed to find 5 inverse in mod 7. So this approach is I am explaining this approach because then you will get a better understanding about what is inverse. හරි මේක ඇඟට ගන්න ඕන. ඇඟට ගන්න ඕන මේ inverse කියන concept එක මොකක්ද කියලා. හරි modular arithmetic වල. Right? Say you are supposed to find 5 inverse in mod 7. Of course you know that we can use the Fermat's little theorem and straight away find out what is the mod 5 inverse. Okay, so let's do it in different way now. Of course that approach we can use. What you can do is, so this is called use of factorizing, right? So what you want to do is you start with 1 mod 7 because multiplicative inverse is all about which number multiplied by this 5 you get 1, right? So therefore we start with 1 mod 7, but now we want to find out if I multiply 5 by which number I get 1. Obviously if I multiply 5 by any number, sorry, I made a mistake. So what you have to start with 1 mod 7, but obviously what we need is something like 5. So therefore what we want to do is we want to find what are the congruent of 1 in mod 7, right? So just listen carefully. What are the congruent of 1 which is in mod 7? Of course 1 is not going to work because 1 cannot be factorized to get 5. Ultimately we want to get 5, right? So from 1 I can't get 5. So therefore what I am going to do is I am going to increase this. In mod 7 8 is also congruent. So 1 is just like 1 we can say 1 and 8 are congruent because we know that 1 minus 8 is minus 7, minus 7 is divisible by 7, right? But unfortunately 8 is not factor or 5 is not a factor of 8 also, right? So we want to do this until we find a number which is a factor of 5 because we are interested in 5. Okay, so therefore still we can't do it. We have to keep moving. So next one, so that means I have to add another 7, right? What is 8 plus 11? 7, 15. Now we can see that 5 is a factor of 15. Why? 15 is 5 into 3, right? 5 into 3. So therefore I can write 15 equal 5 into 3. So now I know that 1 is congruent to 15 mod 7, and I can write that 15 equal 5 into 3 in mod 7, right? Mod 7. Okay, now you know that what is the definition of inverse, right? So what we want to find is 5 inverse. So if you multiply a number by 5, right? If you multiply a number by 5 and if you get 1, that is your inverse. That is your inverse, right? So therefore now you can see that when you multiply 5 by 3 you get 1. Therefore 5 inverse in mod 7 is 3. So that's what you found. So that's a very nice approach, right? So that is a really nice approach, very intuitive approach, very practical approach to get a feeling of what is meant by inverse, right? Of course I don't recommend this to be used in your exam, but this will give you a lot of confidence and understanding about what is meant by inverse, right? So it's a very tactical approach, right? So by definition if you multiply by a number, right, if that results in 1, that is your inverse. So therefore 5 inverse is 3, right? So now we found it, right? Okay, now let's use that approach again for different question. So I want to find 5 inverse in mod 11, right? 5 inverse in mod 11. So let's do it. So how do you start? You find 1 in mod 7. So obviously 5 is not a factor of 1, right? 5 is not a factor of 1. So therefore what you want to find is you keep moving. Now sorry, this is mod 11. So now you have to add 11 to 1, so that is 12, because we know that 1 and 12 are congruent. of 11 in mod 11, because 1 minus 12 is minus 11, minus 11 is divisible by 11. But unfortunately 5 is not a factor of 12, right? When 12 කියන එක දියන්න බෑනේ 5 වරක් මෙච්චරයි කියලා ඉතුරුක් තියෙනවා. So therefore still it's not going to work. Now you are going to add another 11. So 12 plus 11 is 33. So 33 is also congruent to 1, but still 5 is not a factor of 33, right? So you have to keep moving until you get a factor of so sorry, this is not 33, that is 23, because we are adding 11 now. We add 11, so we add 11, so 23. So still it is not enough, then we have to add another 11, because this is not 5 is not a factor. Then you have to add another 11. 33 plus 11 is 23 plus 11 is 34. So 34 is also not a 5 is not a factor of 34. So therefore you have to add another 11. So that is 45. Now you can see that all of a sudden 45 is divisible by 5. 45 is divisible by 5. So now we got that number. 45 is divisible by 5. So therefore I can write it as 1 is congruent to, now 1 is congruent to 45. 45 can be written as 5 into 9, because 5 is a factor in mod 11. Now I want to find the inverse of 5, and I found that when I multiply 5 by 9, it is congruent to 1. So therefore inverse of 5 must be 9. Inverse of 5 must be 9. So that can be done, right? So that can be done. Again, if it is a very big number, you have to spend a lot of time, but this is very intuitive to understand the real meaning behind inverse. Okay, inverse. So this, I have given another example like that. Right, so you can see it is 8. You can start with 1, then add another 19, another 19, another 19. Still they are not 18 is not a factor, but ultimately you will find a factor. 324. Yes, 324 is divisible by 18. Therefore you can say that 324 is 18 into 18. Therefore you can say that actually it must be 18 into 19. I think I have made a small mistake here. So therefore no, it's 18. It's 18 into 18. Therefore in mod 19 inverse of 18 is again 18, right? Inverse of 18 is again 18. Okay, so that is also a very nice approach. Of course you can use the Fermat's little theorem as well. So let's try to use the Fermat's little theorem, because this is anyway prime number. This is prime number, right? So what the Fermat's little theorem says: A inverse equal a to the power p minus 2 in mod p, right? So what I want to find is inverse of 18, that is 18 to the power p is 7 minus 2 is 5 in mod p, right? So now you have to find 18 to the power 5, which is a big number. Then you have to find the mod p. So let's use a calculator. Find 18 to the power 5. (18 to the power 5), that huge number. Then mod 7, which is 2, right? Which is why is that? Sorry, not mod 7, mod 19, right? So I made a mistake here. So this should be mod 19. So I have to redo it. So there's a small printing mistake here. I will update that, right? So there's a small printing mistake. So I'm going to redo it. 18 to the power 5 to the power, sorry, 18 to the power 5 which is this one mod p is 19. Okay, 19, which is again 18. So you can see 18's inverse is again 18, right? 18's inverse is again 18. From Fermat's little theorem we got that 18. Here also we got that it is 18. So there's a small typing mistake here. This must be mod 19. Okay, so because we started with mod 19, I may really mess it up. This must also be 19. This must also be 19. So I will fix it, right? Example 3, right? I will fix it and again upload because I did some changes to this one. Okay, mod 19. So the 18's inverse in mod 19 is again 18. So we got it from this approach. We got the same answer from the Fermat's little theorem as well. Okay, right. Now we are going to discuss the third approach of finding the inverse. So this is the general approach because this can be done only when your mod or your mod value is a prime number, right? Prime number. When p is prime only, this Fermat's little theorem and this approach is going to work, right? But when the mod is not a prime number, right, so you can't use that approach. For that we can use the Euclidean algorithm. But anyway, if the mod is prime number, don't use the Euclidean approach. You can use the Fermat's little theorem, right? That approach is much faster. But if it is not a prime number, we have to use this approach using the Euclidean algorithm. So you know what is meant by Euclidean algorithm to find GCD. So we are going to use the same approach, right? As an extension to the Euclidean algorithm, we can find that same approach to calculate the inverse. Okay, so that this is how we are going to do that. So since we have already familiar with the Euclidean algorithm, it's very easy. Say we want to find inverse of 197 in mod 3000. Now you can see this 3000 is not a prime number, right? So in the world of 3000, what is the inverse of 197? Okay, so what you are supposed to do is, first step is find the GCD of the number and the mod, right? So the number that you want to find the inverse and the mod, find the GCD. Okay, so in this case you have to find the GCD of 3000 and 197. So you know how to do that. Just take the bigger number here and you have to write it like how many what is the multiple of 197, and you can add something that you have to get 3000, right? You have to use it, actually you have to guess. Okay, make 200 radical balance. So in this case you will see that it is 15, right? 15. So you can use a calculator or you can just spend some time, and plus 45. So actually the first few things are the difficult, then it's easier. Then you take 197 here, then you have to say if I multiply 45 by which number, then I can just add something less than 45 to make it 197. You will find that that is 4, that is 180. Then you have to add another 70, right? So then you have to take this 45 here and say how many 17s are there. This is GCD algorithm, we have already discussed. So that is 2, and you have to add another 11. So you have to keep doing like that until you get into 0, right? Until you get into 0, you have to do that. Okay, so then you are done. Then you are done. So that is how we found the GCD. That is how we find the GCD. Okay, so then we have to do another thing. So then that is not the end of it. That is not the end of it, because now our final target is not finding the GCD. Our final target is finding the inverse of 197 in mod 3000. Okay, mod 3000. So now we came up to this point, right? Because now we have stopped it, because next time it is going to be 0 here, right? 0 here, because 1 times 6 plus 0. Okay, so you don't have to go into the last line, right? Now what we are going to do is something like that. So something like back substitution. Okay, so we are going to start with here. Now we have done this one. Okay, so we are going to start with here. So this is another line actually. So these two have nothing to do with. So this is something below this. Okay, just to preserve some space, I have written here like this, right? So we know that 6 is 1 into 5 plus 1. So we can write it. We can take 1 to the other side and say 1 equals 6 minus 1 into 5. Okay, 1 equals 6 minus 1 into 5. Then what you are supposed to do is, to this 5 you can take it from the above one. So you know that 5 is 11 minus 1 into 6. So therefore we can write this as 1 equal 6 minus 1 times 5 can be written as 11 minus 1 times 6. Okay, so still it is 1. You can say still it is 1. So 6, right? So 6, so your 1 equals 6 minus 1 times this. Okay, so therefore you can write it like, so here minus into minus is plus, 1 times 6 is there. This is also, you can take 1 times 6, therefore 2 times 6 minus 1 times 11. So that is how you get this, right? So then you have to substitute this 6 using this one. So you know that 6 is 7 minus 1 times 11, right? So that you can write it like 2 times, right? 6 is 17 minus 1 times 11 minus 1 times 11, right? So that is 2 times 17. Here you have 2 times 11 minus another 11, that is 3 times 11 minus 3 times 11. That is how you get to this one. Then you have to substitute this 11 using this one. So 11 as 45 minus 2 times 17. So you have to keep doing like that, right? You have to keep doing that, like so. Another in another 2 steps you get into this particular thing. So that means you have to get into ultimately you have to substitute this 45 also using this one. Then you get everything in 197 at 197, and this one is now 3000 and 197. So ultimately you get into you solve it until you get 3000 here and 197 here, because last time when you get 45 also you can substitute using 3000 and 197. Now everything is 197 and 3000, right? So therefore what you got is 1 is equal to 533 times 197 minus 35 times 3000. Okay, so that is what you get. So you have to get into this one until you find the GCD. Then you have to go into backtrack, and you have to, from here you have to go this. You have to keep backtracking and ended up like this. Okay, ended up like this. So you have to, every time you have to substitute. So this 5 is, you got to substitute like this. Then this 6 is substitute, 11 is substitute, 17 is substitute, 45 is substitute. So ultimately you get only from with 3000 and 197, right? 3000 and 197. So now your 1 is 533 times 197 minus 35 times 3000. Okay, so that is what you got. So you have to go like that, right? So that step you have to follow. Right, now let's do a clever thing, right? So now we have got this, right? Now we have got this as arithmetic formula. Now we are going to take a mod of 3000 both sides, right? If you have now this number is this number, we can take the mod, because when they have two numbers, its mods are also going to be the same. So that means 1 mod 3000 equal to this number mod 3000. So that from here you get this one. Okay, sorry. So now I'm just scrolling. Now we got this one. it takes a little bit of time, right? A lot of patience as well. And we know that 1 mod something is 1. Right? 1 mod something is 1. Right? For any base, the 1 mod value is 1 because the remainder is 1. Right? So now we can take it as this one as 533 into 197 mod. So I'm just rewriting this. Now this one is anyway 1. 1 is congruent to 533 into 197 mod 3000 minus 35 into 3000 mod 3000, right? So that is a minus b. We can just put it into two mod values. So that is a theorem we learned last time. So because this one is a multiple of 3000, right? So you can see this number is a multiple of 3000. Therefore, this is going to be 0. If a number is a multiple of that mod number, that is going to be 0. So therefore, we can just get rid of this one also. Now we have 1 is congruent to 533 into 197 mod 3000. Right, now we are done. Why? What we wanted to find is what is the inverse of 197 in mod 3000. Right, now we know that when 197 is multiplied by 533, it is congruent to 1. So in that case, our inverse of 197 is going to be 533. So therefore now we found it. Okay, now you can see that why I explain you the previous approach, right? Previous approach. So that is also the same thing. Ultimately, if this is multiplied by this one, if I get 1, that is the inverse of this one. Of course, that approach can be done, but that approach is very long, right? So that is not going to work. If it is a very big numbers, we have to guess next one. So actually what we did is, rather than we guessing these things, we are doing it as a backtracking like this, right? So because this is more systematic. So you can see that ultimately this approach and this approach has lot of similarities, right? So even the final step is like that. If this is multiplied by this one, if it is congruent to 1, obviously this is going to be the inverse of this one. Okay, so that is how you do it, right? So I have given you one more example here. If you are supposed to find 27 inverse in mod 392, again use the GCD algorithm, right? Until you get it into the GCD value or the 0 value, then keep doing the backtracking. Ultimately you will get something like 27 into 363 is equivalent to 1 in mod 392. So therefore what we need is a 27th inverse. When it is multiplied by 363, we get 1. Therefore you can say 27 inverse in mod 392 is 363, right? 363. Okay, of course it can be 363. Why? When the mod is 392, it can be anything smaller than 392. So therefore that value can be 363. Okay, so therefore inverse of 27 in mod 392 is 363. Okay, 363. Right. So likewise, so these things are not that easy to find any other way. And of course, since this is not a prime number, you can't use Fermat's little theorem as well. Okay, right. So any questions up to this point? Because now we are moving to the few more topics. I won't finish. I don't mind whether it's a 12 o'clock or 1 o'clock or 2 o'clock. I want to finish this. Okay, I don't want to do this again. Right? Any questions? No questions. So you are sleeping. I don't know. Either you are sleeping or no questions, or perfectly understood. Whatever. Okay. Right. So we did a lot of things. Right. So we did a lot of things today. So we started with we start. Okay, so we started somewhere here, rule 3, right? So given this, you can either get this one or this one depending on the GCD is 1 or something bigger than 1. Then the Fermat's little theorem in its special case, right? Then how to find the inverse using the Fermat's little and the remainder of a big values using the Fermat's little theorem in a very systematic way. Then the Euclidean Gcd algorithm, the systematic approach of finding GCDs. Then how to find the inverse of a number, and of course what is mean by inverse, right? Then the small test to find whether there's a inverse or not for a given module. Then of course computing the inverse of a prime number when the prime number base is prime number. It's not an inverse of a prime number. There's a small mistake here also. Inverse when the base is a prime number, mod is a prime number, and of course factorizing also you can use. And finally use of Euclidean algorithm to find the inverse of a prime number. Then inverse of a number. Then the mod is not necessarily be a prime number. This is applicable for any mod. This is applicable for any mod. Okay. Right. So this one is not in your syllabus. Chinese remainder theorem. So therefore, I am not going to discuss this with you, but I just add it to the note. If you are curious, you can just have a look at it. Okay, so this is not directly mentioned in your syllabus, therefore I am not going to do that. Okay, but because so usually everywhere when someone is talking about modular arithmetic, they almost all the time discuss about the Chinese remainder theorem. So therefore I just add it. But I am not going to discuss that. I hope they are not going to test your knowledge on Chinese remainder theorem. But if you are curious, it's always nice to go through this, and also you can go to YouTube, and there are so many resources you can use. If you are interested, yes, you can understand. You must be able to understand this without any issue. Okay, but I am not going to do it. I just add it to the note. Okay, anyway, it is not mentioned in your syllabus. Okay, right. So now we have come into the final part. That is solving linear congruence equations, right? Solving linear congruence equations. So that is, still we have been just working with numbers, right? Still it is not algebra, right? Algebra. Now when you are given an equation with unknown value, we want to find out, is there a way to find that unknown value, right? So just like when you are given something like 2x, right? 2x plus 5 equal 1. Now you know how to find x. You know that, okay, 2x equal 1 minus 5, that is 2x equal minus 4. I can divide by 2, then x equal minus 2. So likewise, if you are given something like this, 2x equal 5 mod 3, now can you find x? So that kind of a thing. So only we are going to discuss about linear. So that means we are not going to discuss something like 2x squared plus 5x equal 3 mod 4. No, we are not going to do like that, right? So we are only going to discuss about linear congruence equations. So of course, if you are curious enough, you can find some resources in how to find non-linear quadruple congruence equations as well. But in your syllabus, they have mentioned only about linear congruence equations. That means there are no powers in x, just the power is 1. Okay, right? So it is something like this: ax is congruent to b mod n. Of course, a and b will be numbers. Then you will be asked, what is the value of x? Okay, so this kind of equation is called linear congruence equation. Okay, linear congruence equation. So again, the issue is when you are given something like 2x plus 5 equal 3 or something. Of course you can say 2x equal 3 minus 5, 2x equal minus 2. Then you can divide. You can divide by 2 and say x equal minus 1. But unfortunately, in congruency equations, we can't divide. Of course, we can add the same value. We can subtract the same value. We can multiply it by the same value. But we can't divide. So therefore, solving linear congruency equation is somewhat difficult task, somewhat challenging task. It is not as straightforward as something like this. Again, the issue is you can't just divide, right? You can't just divide in modular arithmetic. You can't just divide by constant. Okay, so now you know why this is challenging also, right? So let's see how to do this, how to do this kind of things. Right, again, when you have a linear congruency equation, there are two possibilities. That is, you have no solution and you have one or many solution. Right. So one possibility is you have no solution. That means when this equation is given, by looking at or by testing, you can say that no, this is not going to have a solution. So that is very happy scenario for you guys, because then you don't have to find it, right? If there is no such thing, you just have to say no such thing, no solution, then you can happily say I am done. So no one is going to come and say please find, please find. So when you say no such thing, then that's the end of the story. But if there is a solution, then we have to find. Okay, so let's look at the happy scenario for someone like someone who don't want to spend a lot of time doing that question. So you just have to check whether there's a solution or not, right? So let's see how to check that. Right, so the congruency equation ax equal b mod n to has a solution if and only if GCD of a and n divides b. So that is this condition you have to check, right? So this is your a, this is your b, this is your n, right? So you have to find the GCD of a and n, right? A and n, and you have to check whether that GCD divides b, right? That GCD divides b, right? So that is, if it divides b, yes, it has a solution. If it doesn't divide b, no, it is not going to have a solution. No, it doesn't have a solution, right? Okay, so let's see. Let's take an example. So in this case, say this is our equation. 2x equal 51 mod 8. So you are supposed to find x. Okay, so now you can, let's write it down again. Two x equal 51 mod 8. So this is my a, this is my b, and this is my n. So this test says find the GCD of a and n. So this one 2, n is 8. So what is the GCD of 2 and 8? If these are very big numbers, you have to use the Euclidean algorithm, okay? But this is very small one. For solving equation, you will be given very small values. So the GCD of 2 and 8 is obviously 2, right? Obviously 2. Now what you have to find, what you want to find, whether that value, right, that value is 2, whether it divides b is 51. So whether 2 divides 51, or you just have to say whether 51 is divisible by 2. Okay, in other words, whether 2 divides 51. So remember this notation we used in the very first day. So I gave you the notation very first time. So you can see this is the notation. A divides b, right? A divides b, or b is divisible by a, right? So that I am using that notation. Right, now let's see. Now you can see 2 does not divide 51. So if this divides b only, it has solution. So now you can see unfortunately unfortunately 2 does not divide 51. So 2 divide, because there's a remainder of 1. So therefore, unfortunately, this particular equation is not going to have any solution. And I know that it is fortunate for you guys, then you don't have to solve it. Okay, right, you don't have to solve it, but let's pretend that it is very unfortunate. So that is, it doesn't have any solution. It doesn't have any solution because 2 does not divide 51, right? So 2 does not divide 51, so our GCD does not divide the b value, right? B value, so therefore no solution. So that is what you have to do, right? Right, so let's take another example. 2x equal 3 mod 6, right? 2x equal 3 mod 6, right? So this is my A, this is my B, and this is my N. So what I want to find the GCD of A and N. හරි මේ දෙපැත්ත දෙන ගන්න මම දෙක නෙමෙයි. ඒක ලේසි මතක තියාගන්න. 2 and 6. GCD of 2 and 6 is obviously in this case also 2. Now you want to check whether 2 divides B, right? GCD that divides, remember, GCD of A and B divides B. B is 3. No, 2 does not divide B, 3, right? So when 3 is divided by 2, it is 1 and remainder 1. So there's a remainder. So therefore 2 does not divide 3. So therefore no solution. No solution, right? So that's it. Right. So likewise, the first thing you want to check is whether it has a solution or not. If it doesn't have a solution, you just have to stop it, right? So this is another example given, right? So you can do that. Right. Now let's move on to the scenario where really we have to solve it. So that means obviously now you know that when GCD of A and N divides B, right? When GCD of A and N divides B, it is going to have one or more solution, right? One or more solutions. So then it is either no solution or one or more solution, right? So obviously if a GCD of A and N divides B, it is going to have one or more solution. You can't say it is no solution. Okay, then we can calculate what is the number of how many solutions are also there. So let's see how to check that and proceed with solving this one, solving the equation. Okay, right. So these are the steps. I have given you two approaches. Okay, two approaches. This is the first approach we are discussing, right? So then I have given you approach 2 also. Approach 1 is sort of a very mechanical approach that you can easily find the solution to any situation. Approach 2 is given for you to understand this, right? So approach 1 is to quickly solve this. Approach 2 is to give you understanding of how this approach is really working. Okay, so practical approach, the practically understand how these things are solved. Okay, so therefore for the exam perspective, approach 1 is more important, right? For those who really want to understand things, you have to concentrate on approach 2 as well. Okay, right. So still we are in the approach 1. So this is now first anyway you have to first find the GCD of A and N, right? GCD of A and N. Then you have to check whether that GCD, so we have just called them D, whether D divides B. D divides B. Okay. Of course, if it divides, we have solution. If D does not divide B, we can just stop and say no solution. But assume that your GCD of A and N, now we call it D divides B, or that number divides B. Okay, so in that case definitely we have solution, one or more solutions. Now let's see how to find those solutions. Okay, so this is how we proceed from that point onwards, right? This is how we proceed from that point onward. So we have to find another value called K, or in number. So we are just giving them numbers, letters, so that we can refer them later. That is, now remember, now we have found D, right? D is basically GCD of your A and N, right? A and N, and also you have found that this D divides B. That is why we are proceeding, otherwise we stop, right? And we found that this D divides B. That means B is divisible by D. Okay, that is what is meant by D divides B. Now we want to find another value. Let's call it K. That is D mod N. Right? So remember we found D. Right? We found D. Now we know what is N. So we want to find D mod N. Right? D mod N. So that gives you the number of solutions that we are going to have. For example, if K is 3, that means we are going to have 3 solutions. If K is 1, we are going to have 1 solution. If K is 2, we are going to have 2 solutions. Okay, so that is how it's going to work. Now you can see that if you are working on a mod 4, right, mod 4, the maximum number of solutions are going to be 3, because always when you have mod 4, the value is either 0, 1, 2, 3, right? So therefore, so you can have something like that. Okay, so if your mod is 3 maximum, it just because it is mod 3, it doesn't mean that you are always going to have solution. There can be a situation where no solution, but if you are going to have solution, there is a possibility of you are getting, if it is mod 3, 0, 1 or 2, or maximum is 2 solutions are possible. Okay, right. So that is how you find the number of solutions. That is your D mod N. D mod N. So therefore, we know that we are going to have K number of solutions. So K number of solutions. Right? Solutions. Right. Now let's see how to proceed. Then I will do example. Divide both sides of the equation, including the mod value. So that is very, very important. Right. So this is very, very, very important. By D. Right. By D. So that is the D that you calculated there. You have to divide this by D, this A value, P value, and not only that, you have to divide the N value also. Right. N value also you have to divide. Okay. Then multiply both sides by the inverse of new way. So it's very important, new way. So once you multiply, you get a new way here. You have to multiply, once you divide by D, you get a different A value here. Then you have to multiply both sides by the inverse of this new way, right? New way. Then the general solution is this one, xk equal x naught plus k times n divided by d. Okay, so that is going to give you the final solution. Okay, and if your k is 3, you are going to have x1, x2, x3, 3 likewise. If your k is 2, you are going to have x1 and x2, right? And for that you have to find x naught. That x naught you find from this stage. I know that this is Greek for you, right? This is Greek for you. Don't worry, right? So this Greek is going to be Sinhala or Tamil or whatever after some in 5 minutes time. Okay, right. So let's take an example. So, right. So once you do the example, you will fully understand this. Okay, there are no hidden things. Okay, so let's take that. Let's take an example. So this is our equation. 4x equal or 4x congruent to 12 mod 18. Right. Sorry, 14x is congruent to 12 mod 18. So they asked us to find what is x. So you can see it's not very. It is not very easy task to guess those things. Okay. Right, this is very difficult task to guess this, right? Of course, if you keep guessing, ultimately you can find it, right? But it's not a very straightforward thing, right? So now let's take it into our format. 14x. Now our A is 14, our B is 12, and our N is 18, right? So what is the first thing we want to find? We want to find GCD of A and N, right? GCD of A and N. So in this case, GCD of 14 and 18. So obviously the GCD of 14 and 18 is 2. Right? GCD of 14 and 18 is 2, because no other number bigger than 2 is going to divide both 14 and 18. Okay. Now we are done with finding the D or the GCD. Now we have to do that test. We have to check whether D divides B. Right. So D is 2. It divides B. B is 12. Yes. 2 divides 12, right? 2 divides 12, or 12 is divisible by 2. Yes, it is 6 and no remainder. So that means yes, we are going to have solutions, right? So we are going to have solution for this one, right? So therefore now we are going to proceed, right? So next thing is, now we know that we have solutions, right? Now we want to find that k. So how to find k? K is our d mod n. So our k is, our d is what? 2 mod, our n is 18, and we know that 2 is smaller than 18, therefore 2 mod 18 is 2. 2 mod 18 is 2. So therefore now we got our k. K is the number of solutions, therefore now we know that we are going to have two solutions. And first we found that yes, it has solutions. By finding k value, we know that there are two solutions. You can see this is not a rocket science, this is very simple, right? This is very simple. Now we are just going to find the zeroth solution, right? Then we are going to find the first solution, right? So that is how we do that, right? So we are going to find the zeroth solution, then we are going to find the first solution. That means two solutions, zeroth solution and first solution. If it is 3, zeroth solution, first solution, second solution. If you got that k as 5, a zeroth solution, first, second, third and fourth solution, right? So luckily we have only two solutions, therefore first we have to find the zeroth solution, then using this formula you have to find the first we are going to find the zeroth solution, then we are going to find the first solution. Okay, now let's see how to find the zeroth solution. Okay, right, so let's see how to find the zeroth solution. So what we are supposed to do now? Now we have come up to point 3, right? Point number 3, divide both sides of the equation including the mod value by d, right? Mod value by d. So that's very straightforward, that's not a big thing. Now we already found that d is 2, right? D is 2. So now what is our equation? So our equation is 14x equal 12 mod 18. So our d is 2. So therefore we are going to divide it by 2. 7x equal 6 mod. It's very important you divide this one also. 6 mod 9. Right. So now we get 7x equal 6 mod 9 because we divided by our d, which is 2. Right, so when you divide this guy by 2, what we get is this one. Okay, right. So now what is the next step says? Now we are done with that. So now we are very close to the answer. The next step says multiply both sides by inverse of new a, right? New a, not the old a, new a, right? So the old a is 14. Old a is 14, right? This is our old a, right? But new way is, now this is our new equation, right? This is our new equation. So our new way is 7, right? New way is 7. So we are going to multiply the left hand and right hand side by inverse of 7. So we have to multiply it by the inverse of the new way. So that means 7 into, right, 7 into 7 inverse x is there is congruent to, so if you are multiplied by 7 inverse here, you have to multiply 7 inverse the right hand side also. 6 into 7 inverse of the mod 9. Now remember we divided the mod also by 2, mod 9. So that is our equation now. Okay, right. So now this is where we have to find the inverse now, right? Now we have come to this point, and we have come to this point. Right. Now we know that when you multiply, now remember we multiplied this by both sides by this one's inverse, new a's inverse. Now we know that when you multiply 7 by 7th inverse in mod 9, right, it is going to be 1. Right? So that is why we multiplied by that. When you multiply this guy by its inverse, it is going to be 1. So therefore this side is going to be 1 times x, 1 times x is x, okay, 1 times x is equal to x, which is equal to 6 times, now 7 inverse mod 9, right, mod 9. Now we have made somehow this coefficient is now vanished, now we have x, right, we have x. Now in order to get the answer, you have to find 7 inverse, in mod 9, right, 7 inverse in mod 9. So that is why we studied how to find inverse value, either using Fermat's little theorem or using GCD approach. Of course here you can't use Fermat's little theorem because this is 9, which is not a prime number. So therefore using the GCD approach or that multiplicative factorizing approach, you have to find what is the inverse of 7 in mod 9. So that you can do it, right, that you can do. We already explained how to find those things, right, using the Euclidean approach or factorizing approach. That you will find that inverse of 7 in mod 9 is 4. That you have to do it, right, you have to do it Euclidean approach or whatever. That is 4. So therefore you can write x is congruent to 6 into 7th inverse is 4. That you have to find using that what any approach. 6 into 4 in mod 9. So 6 into 4 is 24 mod 9, and we know that 24 is bigger than 9. Therefore you can just take what is the value, 24 divided by 9, what is the remainder. So that is 24 divided by 9. What is the remainder? That is 2 is 18. Then 6 is remaining, right? 2 and remainder 6. Therefore you can say rather than 24 you can say 6. Right? Rather than 24 you can say 6. So therefore answer is 6 mod 9. So that is our first answer. We call it zeroth answer. Right? We call it zeroth answer, or we can just call it x0 is 6 mod 9. Right? 6 mod 9. Now we have found the first answer or the zeroth answer, and we found that according to K it says there are 2 solutions. Now to find the other solution, we are going to use this formula. Right? We are going to use this formula. Just we have to use only once because we know that there is only one more solution, right? There is only one more solution, so we are going to use that formula. Okay, right, so this is the formula that we are going to use. Xk equal x naught plus k times n divided by d, right? So we have already found x naught, and we know what is n, that is a mod, but here you have to use the original mod. So that is something you have to remember. So this is now original mod of the original equation, not 9. Originally the mod was 18, right? So you have to use the original mod now. So therefore n is 18. D also we have found, right? D also we found, that is the GCD value. In our case the D is 2. And also now don't get fooled here. This k is not the k that we calculated previously. Remember we calculated something called k to find how many solutions are there. No, this is not that k. This is just right, this is just this particular k. So this says xk, right? So this is x1, x2, x3, etc. So what I need is x1. So therefore k is 1. So therefore here k is 1. So this is not that k that we calculated. So therefore in this case k is 1. So now x0 we found, right? That is 6. So therefore this is 6. Plus we are finding the first solution x1. Therefore k is 1. N is 18. D is 2. Then you just substitute this and you calculate, you get 15, right? You get 15. So the answer is therefore 15. So I made a small mistake here. So this must be also finally not mod 9. The final answer must be in mod, because originally the question is about mod 18. So therefore the final answer must also be mod 18. So therefore now we found the 2 answers. The 6, right, 6 and, so that is the x0, 6 and, so just now we found 15. So those are the 2 answers. and we know that there are only two answers, right? There are only two answers. So the origin x0 we found by using this formula, substituting k as 1, we found 15. So those are the two answers. Those are the two answers. Okay, right. So let's see whether the answer is correct anyway. 6 and 15, just substitute one value and see whether it's a valid answer. 6 and 15. Right, so let's take, so what are the two answers we got? 6 and 15. 6 and 15. Okay, so let's take something like 6 here. That is 14 into 6. We have to check whether it is congruent to 12 in mod 18. So let's use a calculator. Okay, let's use the calculator and see whether that answer is correct. See, 14 into 6, which is 84. Let's see whether 84 mod 18 is same as 12. Mod 18. Yes, that is 12. So you can see that is answer. That satisfies. So let's double check the second one also. Right. So second one is 15. So 15 into 14. 14 because x is 15. Let's take 14 into 15. 210. Let's take the mod of 18 and check whether that is also 12. Mod of 18. Yes, that is also 12. So therefore 6 is an answer, 15 is an answer, right? 6 is an answer, 15 is an answer. So both are answers. Okay, so you can see it's very difficult to guess and find that. Okay, so so if it is something like 300, 500, so you have spent a lot of time. Okay, but if you follow these things in a systematic way, you are definitely going to get the answer, right? So let's quickly do another example, right? So 9x equal 42 mod 6. So let's see, 9x equal, so not equal, congruent to 42 mod 6. Now our originally a is 9, b is 42, n is 6. So first thing what we want to do, find the GCD of, so we call it the GCD of a and n. 9 and 6. Now you can see the biggest number that divides both these numbers are what? 3. Right, 3. Because 6 is divisible by 3, 9 is divisible by 3. Now we are done with D, right? So now we want to find now we want to do that check whether we have solution or no solution. That is whether this D divides B, right? So let's say whether D divides B. D is 3, whether it's divide B, which is 42. Yes, 3 divides 42 because 42 divided by 3 is 1 and 14, right? Yes, 14. So the answer is 14 without remainder. So that means yes, we are going to have solutions. So the next step is what? If they are going to have solution, find the number of solutions. So how to find the number of solution? So you don't have to memorize now. Then right? So we call it K. Apna confused right? Say this is K. So we can say K equal this particular D in mod n. Right, mod n. So in this case our D is 3, mod 6. So 3 mod 6 is 3. So that means we are going to have 3 solutions. So we are going to have 3 solutions, right? Then 3 solutions. So how to find the first solution or the zeroth solution? So I'm going to delete this. So you have to divide it by D, right? So original equation you have to divide it by D. In our case we got D as 3. So therefore 9x is congruent to 42 mod 6. You have to divide it by 3 everything. So 9 divided by 3 is 3x, right? 42 divided by 3 is 14. 6 divided by 3 is 2, right? 6 divided by 3 is 2. So therefore now our equation is reduced to 3x is congruent to 14 mod 2, right? 14 mod 2. Now what we are supposed to do? We are supposed to multiply both sides by inverse of a, new way. So our new way is 3, so we are supposed to multiply, so this side 3 into 3 inverse, x is still there, 14 into 3 inverse, mod 2, right? Now we know that 3 into 3 inverse is 1 in mod 2, therefore it is going to have only x here, right? x equal 14 into 3 inverse mod 2, right? 14 into 3 inverse mod 2. Now in order to proceed, what you are supposed to do, you want to find what is the inverse of 3 in mod 2, right? What is the inverse of 3 in mod 2? That is not a difficult thing, you can even guess and find, right? And of course you can use the Fermat's little theorem as well, because 2 is a prime number, right? So you will find that that value is 1. So therefore 3 inverse in mod 2 is 1, right? Anyway, this 3 is also, you can consider it as 1, right? So 1's inverse is 1, right? So therefore anyway it's 1. So therefore you get x is congruent to 14 times 1 in mod 2, right? So that is 14. Now the 14 is bigger than 2, so therefore you have to find out what is this value. You know that that value is going to be, it is divisible by 2, that means that value is 0, right? Because 14 is divisible by 2, that means that value is 0. So therefore now we got the x naught value, as 0, right? As 0. Now we are going to use this formula to calculate. Now we know that there are 3 solutions, so therefore we are going to now calculate the x1 and x2, right? So how to find x1? So now k is 1, our x naught is 14, sorry, x naught is 0, x naught is 0, this is the value we got, x naught is 0, k is 1, and n is that original n, 6, and d is that original d, 3, right? So now we got x1 as 2. Now we are done with x1 also. Now again we are going to do the same equation, but k equal to, because we know that there are 3 solutions, right? So 3 solutions. So x2 is x naught, still the x naught is x naught. Now the x naught is still 0 plus k is now 2 times n divided by d, anyway that is the 6 divided by 3, okay? So that we got as 4. So now we are done, because we know that there are only 3 solutions, right? There are only 3 solutions. Therefore what are our solutions? 0, 2 and 4. So the answer is 0, 2 and 4, right? Actually it is not mod 2, again small printing typing mistake. Originally it is mod 6. So the answer is 0, 2 and 4 in mod 6. 0, 2 and 4 in mod 6. So that is our answer, okay? 0, 2 and 4. 3 answers are there. So x can be 0, x can be 2, x can be 4. 0, 2 and 4. Yeah. Let's double check one of the answer. Oh, right. So let's double check. Okay, I deleted everything. 0, 2 and 4, right? 0, 2, 4. Right. So if it is 0, 0 is congruent to 42 mod 6. That is correct, right? Because 42 is divisible by 6. 42 is divisible by 6 means what? Yes, 0 is answer. 0 is answer. X can be 0. Let's make it 2. If it is 2, 9 into 2 is 18. 18 is congruent to 42 mod 6. Let's see whether that is the case. How to check that? 18 minus 42, is it divisible by 6? If so, this is the answer. 18 minus 42. Now it's getting closer to 12, so my mind is not working. So therefore I am using calculator more and more. 18 minus 42. So 42, which is minus 24. Obviously minus 24 is divisible by 6, right? 24 is divisible by 6. So therefore, yes, that is an answer. That is an answer. So the third one, it is 4. Right? 4. So let's double check that. 9 times 4, 36. 36 congruent to 42 mod 6. So 36 minus 42 is obviously 6. Yes, therefore that is also answer. So those are the 3 answers: 0, 2 and 4. Right? So I did examples having no solutions and many solutions. I did 2 examples. First one was having 2 solutions, the 0th one and the first one we took from the formula. The second example was having 3 solutions, the 0th one, and using the equation we found 2 more solutions. Okay, so there's another one given, so you can try out that one. Okay, that one is also having 3 solutions. Okay, so that one you can try out by yourself, and you can go to the internet and find so many quizzes and questions with solutions. You can try out those things. Okay, right. So now we are done. Actually, for those who have the curious mind, I will take another 10 minutes. We can finish at 11. So I wanted to finish it 11. So we can finish it at 11. So this is approach 2. This is to make it little bit more practical or intuitive, because this is more mechanical, right? This is more mechanical thing, right? So this approach, because I never explained you why we want to divide it by d and how this solution came, etc., etc., right? So these are just came from the sky, right? So this is for curious mind, just to understand how this approach came, right? How this approach came, little bit of how this approach came, right? So let's do in a different way. Of course, in the exams you can do the previous approach, especially if it is if you have big numbers, because this approach need little bit of guessing also, but this is more systematic approach, more practical approach. Okay, so let's say we want to solve 2x is congruent to 3 mod 7. Of course, this is very simple one, right? So this is how you do that. So the first part is anyway the same. You just have to find the GCD, right? GCD of A and N. So in this case, you know that A is 2, B is 3, N is 7. So find the GCD of A and N, 2 and 7, which is 1, right? And we know that when it is 1, of course, not when it is 1, in mod 7, actually that step I skipped. In mod 7, right, so you have to find the d equal 1 mod 7, which is anyways 1. So therefore we know that it has one solution, right? It has one solution. Now let's see how to find that solution, right? How to find that solution without using those formulas, so dividing by that d value, etc. Okay, so now what we are going to do is we are going to start with that identity. We know that in mod 7, 1 is congruent to 8, because after 1, when you add 7, what you get is 8, right? So that is normal, right? So we always start with that identity one, right? 1 is congruent to 8 mod 7. Then we can write 8 as 4 into 2, right? 4 into 2. So why we are interested in 2? Because you can see there is 2 here, right? So therefore I can write 8 as 4 into 2, right? 8 as 4 into 2. So therefore what we are going to do is we are going to multiply it by 4, right? So therefore what happens is this is our 1 equal 8 mod 7. So this one is so this formula we are going to multiply it by 4. This formula we are going to multiply it by 4 because we can't divide. Therefore what we are going to do is we are going to multiply, right? So we are going to multiply it by 4. So the 4 into 2x equal 4 into 3 mod 7, right? 4 into 2x equal 4 into 3 mod 7. So in that case what we get is 8x, right? 8x equal 12 mod 7, right? 8x equal 12 mod 7. So now we know that when now 8 is congruent to 1. So that is why we want to get 8 here, right? So of course from here you can't get 1, but from here, rather than try to get 1 here, because we can't divide by a number, right? If we can divide by a number, that is really easy, right? You can just say divide by 2 here, divide by 2 here, now I find x. But this is a trick. Rather than making it 1, because we can't divide a formula by a value in modular world, what we try to do is, rather than making it 1, we try to make it to the next bigger value, because we know that 1 is congruent to 8. Therefore, by multiplying this by 4, we make it 8x, right? Rather than dividing, because division can't be done, right? So because we know that 1, the next congruent value is 8, so therefore we make it to 8x, and we know that 8 is congruent to 1. So therefore, rather than 8x, I can say it is 8, because 8 is congruent to 1. So therefore, now what I got is x is congruent to 12 mod 7, right? X is congruent to 12 mod 7, and of course we know that 12 is bigger than 7. So therefore, we can simplify it and say rather than 12, I can say it is 5. Right? It is 5, because when 12 is divided by 7, the remainder is 5. So now I got the answer. Right? Now I got the answer. Okay. So now again, what is the idea? So because this is a congruent equation, you can't divide by a number. So therefore, we try to figure it out. What is the next bigger number which is equivalent to 1? So the next bigger number is 8. Therefore, we try to make this somehow make it 8. Then it's something like 1 again. Right? So you can see this is a very clever trick. It's not a trick actually. It's a very clever tactic to solve it without dividing by a number, because you can't divide by a number. Okay, right? Then someone will ask, if you can't divide by a number, how in the world you divide here? I ask you to divide entire thing by 3, right? Even the mod value, right? Entire thing by, in this case, in this case 3, entire thing. This 6 is divided by 3, 15 is divided by 3, 21 is divided by 3. Yes, so you can see that it's a trick that we did, right? So when we are dividing, we divided by a very specific number actually, right? Not just any random number. We divided it by a very specific strategic number. So when you divided by that number, it is not going to harm. And again, therefore we divided both, even the modulus as well, right? But in this case, when you solve it like this, we are not dividing. We are keep on multiplying, because multiplication is okay. Multiplication is okay, but we are going to multiply it to get into a number which is equivalent to congruent to 1. Okay, right? So I have given you another 2 examples. So let's look at this one, and we are finishing. Third one I am keeping it to you. Say 5x equals 6 mod 9. Right? 5x equals 6 mod 9. Now we have to find the GCD of 5 and 9, which is 1. So that means one solution is there. Right? One solution is there. So now again I write in mod 9, 1 is equivalent to 10, because 1 plus 9 is 10. So therefore, let's try to make 5 go into 10. So how to do that? You have to multiply it by 2. Now you can see this approach is also not that difficult, right? For simple things, actually this approach is much easier and very intuitive. So 5, if you want to make it 10, because we know that 10 is equal to 1, you have to multiply it by 2. But you have to multiply both sides. So multiplication is okay, right? Multiplication is okay. So therefore, 2 into 5 is 10x equal to 12 mod 10, and we know that 10 is equivalent to 1. So therefore, I can just say 1x equal to 12 mod 9. And 12 is bigger than 9, therefore you can just divide by 9 and give the remainder. The answer is 3. Right? For simple things like that, always use this approach, because this is much more intuitive approach. We are not dividing, right? We are not dividing. Okay. So we'll take another example. Anyway, that is our final example. 12x is congruent to 17 mod 19. Right. So again we have to find the GCD of 12 and 19, and you will find that again that is 1, because 12 and 19 are relatively prime numbers. So that means we are going to have one solution. Okay. So again we have to find out Now remember, 1 is congruent to which number? So now remember, now I have 12. Now I have 12. If I multiply 12 by which number, I will get something congruent to 1. So which one are the congruent values? 1 is congruent to 20 because 1 plus 19 is 20. But if I multiply 12 by a number, I am not going to get 20. So therefore, no. So then I am going to the next level. 20 plus 19 is 39. No, I can't multiply 12 by a number and get 39. So I am going to the next one. Next one, no, 12 multiplied by any number, I am not getting 77. The next one, 96, yes, I am getting 96 when I multiply 12 by 8. So therefore, I know that 96 is congruent to 1. Therefore, I am going to multiply 12 by 8 because I know that then it is 96 which is congruent to 1. So therefore, I am multiplying this equation number 1 by 8 so that I get 96. I know that 96 is congruent to 1. So then other side, then in this approach we don't have to find the inverse, right? So the 136 is the value. So therefore 136 mod 19 is, because 136 is bigger than 19. 136 divided by 19, what is the remainder? That is 3. Okay. So that approach is also going to work. So likewise, when things are getting bigger and bigger, you have to keep guessing, keep trying. So therefore, you can see this approach is going to not going to be very efficient, right? But the other approach is much more efficient, because we are making it in a sort of a formula to calculate the values. Okay, but better understand both the approach, and in the exam, if it is somewhat bigger value like this, you can always use this approach. Or if you feel like it is possible to, after 3 or 4 steps, if you can find the value, you can use the other approach. Okay, right. So in this approach also, you can see that so why we want to multiply it by inverse, right? Why we want to multiply it by inverse? Just to make this 1, right? So otherwise there's nothing. We, rather than dividing, we multiplied it by the inverse just to make it 1. Okay, right. So we are done with your syllabus and we did everything, right? I didn't do the Chinese remainder theorem because it is not mentioned in your syllabus, right? So I hope you get something, right? So at least you understood what is my modular arithmetic, why we are doing those kind of things, modular arithmetic, because especially those things are heavily used in security. And of course, modular arithmetic must be difficult. That is why we use it in security, right? So we want to, when we are encrypting, we want to do it in a very difficult way so that others can't easily guess it, right? So obviously that is why we use modular arithmetic rather than normal arithmetic to encryption, decryption. Okay. So therefore, obviously this is difficult subject, right? Difficult topic, but it's very interesting topic. And those who have done maths, A-level maths, they have already seen that this is something like matrix. We have the concept called inverses. In matrices also we are solving linear equations. Here also we can solve something like linear equation. Here also we are multiplying by inverse to solve that equation, right? So there's a very nice pattern here, right? So anyway, others also will learn, will see that pattern when you are doing matrices in your final year maths. Okay, right? So we are going to stop at this point. So if you have any questions, you can just put it into the WhatsApp group or any other questions or whatever. So I will be I have already uploaded this document to the Google Classroom. I found there are three places small typing mistakes, not typing mistakes, my mistakes are there. I will make those mistakes or correct those mistakes and re-upload it maybe tomorrow morning. Okay, right? So we are going to stop at this point, right? Thank you.